Okay, so this is a continuation of the problem, the solution of the problem that we have started yesterday. Let's just remember this. We have an elevator here. We have an elevator which goes up with this velocity, moving with constant velocity. Right at the time when the floor of the elevator is at the same level as the ground in here, we throw a ball from the ground in the upward direction. Its velocity is 8 meters per second. And of course, this basically falls down on the elevator later. And we are asking for the velocity of the ball immediately before it hits the floor. So I'm going to repeat the solution again. So, but there are these two frames in here. So that's the ground frame, in which case the ball has an initial velocity of 8 meters per second. So it just goes up and down in here. So it has some final velocity in here. So that's VB prime. And that's the one that we are asking for. And then, all right, that's basically the frame of the ground, basically. But we can also look at this problem from elevator's frame. In the elevator's frame, the ball is thrown upward with an initial velocity of 5 meters per second. Okay. From this level, and it basically falls on the same level. So therefore, the final velocity, yeah, let me just write it down like that, right? So that's V prime VE is therefore minus 5 meters per second. So this is something that I can immediately find. And then I say that, well, I think I should add that I have been using the y-axis to be pointing upwards. So that's also given in the problem. So in any case, so V prime BE is, these are just components, just keep this in mind. So as a result, I need to use these signs consistently. So this is 5, minus 5. I would like to find this one. And the elevator's velocity is plus 3. So therefore, this is this then gives me V prime B to be equal to minus 2 meters per second. Okay. So therefore, then we say that the final velocity is basically 2 meters per second downward when it hits the elevator's floor, right? In any case, so the problem is actually stated and asked in this frame, but to solve the problem quickly, we needed to pass to another frame, right? So is it worth it? In some cases it is, because there are some situations where the physics is actually quite simplified. And so as a result, we actually do this, right? This is one type of reference frame transformation that we do a lot, right? So in that case, one of the frames is moving with constant velocity. So we pass that frame, look at the events from that point of view of that frame, and then after solving the problem, we go back, right? So it's actually quite useful. As I said, I mean, this is something that we use a lot, especially in these particle collision experiments, right? So sometimes, I mean, usually you would think of it like there's a stationary particle, a nucleus, for example, atomic nucleus, and an incident particle hits to this, and then, I don't know, something else is produced, right? So they just scatter off. In any case, so this is the lab frame, for example, but sometimes we would like to pass to this centromess frame where they are both approaching to each other, and then, well, they scatter off. So that's called the centromess frame, for example. Right? That's one of the tricks that people use a lot. And for this reason, I'm going to concentrate on these kind of things. So when time comes, I'll talk about different things, different physics, different physical phenomena from these different reference frames. So let's just look at these things, for example. What's the time, let's say, time of flight? Okay. So I can easily answer this because this is the initial velocity. So let me say it like that, all right? So there's an initial velocity, and there's an acceleration, which is minus g. And I need to compute the time from here. So final velocity is minus 5. Initial velocity is plus 5. Acceleration is minus 10. So therefore, time of flight is 1 second. Okay. So this is from the elevator's reference frame. But from the ground frame, I can compute it like this. So the final velocity is equal to initial velocity plus the acceleration times t. So this is minus 2, this is plus 8, and then I have minus 10 in here. So in here too, I'm going to get t is equal to 1 second. Okay. So as a result, in both frames, some of the answers are the same. So these are called the let's say it like this, quantities which have the same value in different reference frames are called invariants. Right? Let me add so that this is a perfect English. So a quantity which doesn't change. So time is something like that. So this is basically Newton actually formulated this. So the let's say it like this, in Galilean relativity, time is absolute. It's the same for everyone, so that means it's invariant. So as a result, if I just compute the time, I mean, compute some kind of a time difference, let's say, right? The time that the ball hits to the ground, for example, I'm going to find the same value independent of which reference frame I use, okay? So these are invariant quantities. Let's say it like this. This is the second thing. So quantities which change value, which change value in, let's say, different frames are said to be relative. Right? These are relative quantities, like velocity. For example, velocity, position, etc. are relative. All right. Normally, the acceleration would also be relative because we know how the acceleration transforms. But for that special case, since the frames are not accelerating relative to each other, the acceleration is also not relative in here, right? So every particle have the same acceleration in both reference frames. All right, in any case, so we will see later that energy, for example, is also one of the relative quantities, okay? And then there's something called, formulas which does not change form, which do not change form, are said to be covariant. Right, that's a word that you don't need to know right now. I'm just saying this because sometimes people confuse these. So quantities that have the same value are invariant, but the formulas like this, like the final velocity is equal to the initial velocity plus the acceleration times t. So that's a covariant formula. So it's basically a constant acceleration motion in both frames. So therefore, this formula is said to be covariant. But in a different reference frame, I'm just going to insert in different values for these things. And so as a result, the formula is used in a different way. but the form of the formula is the same. So again, in here, I have used the same formula in this reference frame and then that reference frame with different numbers. So the formula is covariant, time is invariant, and the velocity are relative, right? I mean, this is just for setting the some common terminology that we use. Okay, so let's go to the part B. So at which time does the ball reach maximum height? So finding the maximum height problem, and we would like to find what the maximum height is, right? And what's the maximum height? But I'm going to do this in two different reference frames. But in any case, I'm just going to start with, yeah, I mean, I'm just going to do the part B in here. So the question is something like that. So let's say that I solve the maximum height problem in which reference frame? Let's say relative to elevator. Right, elevator's reference frame now. So in that case, the ball is thrown up with an initial velocity of, was it 5? Yes. VBE is equal to +5. I need some space. So VBE is equal to +5 meters per second. All right, that's the initial velocity. Right, it reaches to maximum height and then comes back and then hits to the floor again. So the hitting time is basically is equal to 1 second. So therefore, let's say at the topmost point, therefore the time is equal to 0.5 seconds, right? Because of the symmetry of this motion, the upward motion and the downward motion. Okay, so yeah, I'm on the right track, all right? So I thought that I missed something. No, I didn't. So what's the maximum height? I can actually compute this somehow like that. So let me write it down like that. So the maximum height, how do I find this? I don't know. Let's say that delta y is equal to, sorry about this. This is VBE, all right? Let me use the correct terminology. Delta y is initial velocity times t, which is the time to reach to the top, plus 1/2 of the acceleration times t squared. Okay, so let me again shift to towards left. So initial velocity is +5. The time is 1/2. And then I have like 1/2 of -10 in here and then 1/4. So that's a little bit difficult calculation. So that's -5/4. So that's 5/4 meters. So that's 1.25 meters. Okay. So that's the maximum height then relative to the elevator, right? So somebody in the elevator is going to see this ball rise to that height and then fall back to the ground again. Okay. So then let's just solve the same problem. So that's the maximum height relative to the ground. Okay. So that's the second part. So let me underline this. Okay. So in that case, let me do it like that, right? So the initial velocity is +8 meters per second. And then it just goes up and then falls somewhere in here. So you can kind of see that the time is not the whatever. So in any case, so let's just write it down like that. So let's say it like this. VB is equal to 0. Let me say double prime at top point. So therefore, VB double prime is equal to VB plus minus G times T. I need to solve this equation. So this is 0. This is +8. This is -10 times T. So the time to reach to the topmost point is equal to 0.8 seconds. All right, so there's this first surprise in here, but let me quickly do the calculate the maximum height as well. But this time I'm going to use this thing in here. Yeah, I don't know, let me call this as H prime. Yeah, whatever. I mean, yeah, I don't want to do this. So that's the reason. So in any case, VB double prime squared minus VB squared is equal to 2 times the acceleration times delta y. Delta y is H prime, right? I'm going to use this equation. So that's 8 squared, and then we get minus 20 H prime. This is 64, so H prime is equal to 3.2 meters. But this is from the ground. If you want to find the elevator, the distance from the elevator, in that case, you have to subtract the position of the elevator. I'm not going to do this, so that's not the important point. Important point is, we said that the time is absolute, but here I found the time to reach to the maximum height is different than the time to reach to the maximum height in here. And the question is, why are they different? Why is this relative? It is a simple answer, obviously. But in any case, I hope that everybody found the answer. So
is
again,
it according to final position of elevator, right?
Final position of what?
Elevator. 1 point.
No. The maximum height, the time to reach to the maximum height relative to the elevator is different than the time to reach to the maximum height relative to the ground. And the question is why? Yes, velocity is different, right? So that's, in any case, so let's just remember this maximum height time. Sorry, height time. The problem is this. So the question is basically, what is the time when the velocity becomes 0? So that's when we solve the problem of maximum height, if you want to solve the problem of the time to reach the maximum height, we're so asking this problem, when the velocity becomes 0, what's the time, right? But the velocity is relative, right? This thing is relative. And so as a result, in different reference frames, we are going to find different answers, obviously. So I'm just going to explain the reasoning in here in terms of the, so this is position relative to the ground. So let's say y relative to ground, right? So this is the position versus time graph of the elevator. So that's the position versus time graph of the ball, right? So that's the hitting time, right? The hit. Okay, so what I have said is that, all right, the ball reaches to the maximum height at the time 0.8 seconds. Well, the hitting time is 1 second. So at 0.8 seconds, it reaches to the maximum height. That's all right. But when does it reach the maximum height relative to the elevator? When the ball has a velocity which is equal to the elevator's velocity, if you look at it like that. So basically, it is that point in here where the slope of the curve is the same as the slope of the, yes, that point in here where the slope of the curve here is the same as the slope of this line in here, right? So at this point, basically the distance of the ball relative to the elevator or the distance of the ball from the ground, the floor of the elevator is maximum, right? What you do is like, there's a line in here, right? This is line. You just draw a parallel line to that one. So we just draw a parallel line. And I just shift this parallel line in such a way that this line still passes from this curve in here. But now this distance is maximum. So this is max, right? I would like to maximize that distance, right? And this can only happen when the second line that you have drawn is tangent to this parabola, right? You can also think of it as a mathematical problem like that, okay? So in any case, what I'm saying, yeah, let me actually do it like that. So this is the point where the maximum height condition is satisfied relative to the elevator. And this is the point where the maximum height condition is satisfied relative to the ground. And these are two different points. Okay. So yes, the times are 0.5 and 0.8 seconds. Okay. The lesson. What's the lesson? Why did I spend so much time on solving this problem? The lesson is, right, if you look at the description of the motion in these two reference frames, they are going to describe the motion differently. I mean, the two people in the reference frame, they are going to describe the motion within that interval of time in a different way. So relative to the elevator, within that time interval, the ball is going down. So therefore it is falling. But relative to the ground, the ball is still going up. Okay. So I think this is important because I know that some of you have some conceptual mistake like this. So again, let's just concentrate on this. So some people, when they look at this free fall motion, they tend to separate the part of the motion where the object is rising from the one where it is going down. But these two motions are not different from each other because in a different reference frame, it is possible that the object is rising during the whole time. Yet in another reference frame, the object might be falling during the whole time, all right? So as a result, you basically separate this motion into these two parts, but the projectile doesn't do anything different in any part, right? Whether it is rising or going down, this is a relative thing, okay? And that's the reason why I call the whole motion as free fall motion. So even when it is rising, we call it as the free fall motion, right? But we don't actually see any problem with this, right? It is rising, but we say that it isn't free fall. That's okay, because we know that at least with respect to some possible reference frame, this object is really falling, all right? And when it is falling, for example, relative to my reference frame, it might still be rising in yet another possible reference frame, right? So let me say it like this. Whether the ball is falling or going up is relative. Okay, it depends on the reference frame used. And later we are going to see that using the elevator's reference frame is justified. So that's actually a very perfect reference frame because of the relativity principle. You can really use it as a reference frame because all the laws of physics are covariant. They have the same form within the elevator frame as well. So as a result, it's one of the perfect possible reference frames as well. Okay. Yeah, from the reference frame of the ball, it hasn't moved at all. But the reference frame of the ball is an accelerated reference frame that we are going to see that there is a problem with that reference frame. But when we see this dynamics, I'm going to discuss this, right? Basically, the reference frames which are moving with constant velocity relative to each other are somewhat okay. But if they are accelerating relative to each other, then there's small problem in there that I'm going to discuss later, right? But that's just an introduction to the topic of the relative reference frames. Okay, I mean, that was the whole purpose of that exercise. I mean, the direction of the motion is relative, just like the velocity is relative, the direction of the motion is relative. So as a result, don't separate these into these two parts. So, I mean, if you want to solve these kind of problems, for example, I give the initial velocity, for example, and I ask for the time of flight, for example. Don't separate this, or I don't know, find the velocity in here. Don't separate this into these two parts. I know that some of you do because somehow you have learned it that way, but it is unnecessary to actually compute the, I don't know, the properties of the motion at the topmost point. So you basically have some initial point and some final point in here. You just need to write down a second order equation, polynomial equation, but that's the only difficulty. I mean, apart from that, because I know that when people divide the problem into these parts, they start making mistakes one way or the other one. It's not always the case, but it is possible to do more mistakes if you do more calculations. Okay, and that's the reason why I'm doing this. Okay. So this is the second one. So you can think of it as a one-dimensional relative motion example. Here, again, there is no free fall and things like that. So as a result, it's just a simple, straightforward application of the relative motion concept, right? Let me actually say it like that. Okay. So in any case, we have a boat which has a top speed of, right, it's given to us, is 6 meters per second. And people ask, what does that mean? What does that 6 meters per second mean? Is it relative to water or relative to the ground? All right. And I find it hard to explain why this has to be taken as 6 meters per second, because nobody bothers specifying the velocity of boat relative to a ground, because the boat has no contact with the ground, right? So I don't know. I mean, what's the velocity of the boat with respect to some, I don't know, airplane, for example? Nobody can would like to specify this. And when you want to specify the top speed of a boat, you don't specify it relative to something, right? In any case, so since the boat is moving inside water and it basically pushes itself forward in the water by just interacting with water, that's always relative to water, all right? Just keep this in mind. So in any case, we have this kind of a boat, but I would like to use it in a river. The river is actually flowing with a speed of 2 meters per second. So that's the downstream direction. And there are two houses on the same bank of the river, right? The distance between them is 8 kilometers. And I would like to go back and forth between these 2 points. So first, I would like to go from A to B, and then from B to A, right? And I'm asking basically the travel time, right? That's a very simple exercise, but I'm just going to quickly do it in any case, okay? So what's important in here is that, I mean, sometimes people, by using their intuition, they can find the relevant speeds quickly without, by using mental calculations only, right? If you are comfortable with this, I think that's okay. But here, we would like to use the formalisms of the formalism that we have used. We have developed for the relative velocity. So as a result, we are going to have these two reference frames, right? I'm just going to use the W as the water's reference frame. And then so therefore there's some kind of a point in here, which is the origin in here. You can think of it as some kind of a, I don't know, the wood, which is basically flowing with the water, and somebody on the wood, some ant perhaps, is looking at the events from their own perspective. There's another reference frame in here, G. I'm going to use for this for the ground. Okay, so in any case, A and B are, yeah, what should I use? Yeah, I'm going to use X. I'm going to use P for the boat, right? P is the boat. Let's think of it as a particle point boat. In any case, I'm using A and B for these houses. So as a result, these are already taken. In any case, I'm just going to use this symbol VP for the velocity relative to ground. Okay, so the idea in here is that I know this. This is known. I mean, the velocity of the boat relative to water is known. Well, we know that its magnitude is 6 meters per second. The direction of the motion changes. So depending on the direction of the motion, this has a positive or a negative sign. So in any case, so this is known. And by using this, I need to compute this, the velocity of the boat relative to the ground. Okay. So let's just do it like that. So therefore, velocity of the boat relative to water is velocity of the boat minus the velocity of the water. So these are relative to the ground. To make it easier to read, I didn't add the letter G in here, right? Just keep this in mind. Okay, so I need to use this equation, but yeah, this value is different for both cases. So let's say part A, let's say travel from A to B, right? It is that travel in here. So whatever. In that case, since my x-axis is downward, I know that the velocity of the water, velocity of the boat relative to water is plus 6 meters per second. And so in any case, so if I just use this equation, right? So that's plus 6. I don't know what this thing is. And this is plus 2. So from here, then we find the velocity of the boat to be equal to 6 plus 2, 8 meters per second. And so as a result, the travel time is the distance traveled divided by P. The distance is 8 times 10 to the 3 meters. And the velocity is 8 meters per second. Yeah, whatever, that's going to be like 1,000, yeah, 10 to the 3 seconds, right? So in any case, let's quickly do the other problem. So we are traveling from B to A, right? So in that case, this is the way that we go, all right? Our x-axis is still in towards right. In this case, the velocity of the boat with respect to water is minus 6 meters per second. And we use the same equation again. So that's minus 6. This is VP, and this is still plus 2. And so from here, we find the velocity of the boat to be equal to minus 2 meters per second. The time to reach in that case is, this time the displacement is negative. So that's basically displacement delta x divided by the velocity, right? I'm using this formula in here. Okay. So in any case, both are negative. So therefore it's like minus 8 times 10 to the 3 divided by minus 4. Excuse me? 2 times
minus
10.
4.
Excuse me?
It's minus 4.
Why is it minus 4?
VP, sir.
VP is minus 4. Ah, yeah. Sorry. Yeah, I used the minus 4 in here, but okay. So thank you very much. Yes, so it's 2000 seconds. All right. Thank you very much. Okay, so that's it, basically. So in any case, this is an example of a one-dimensional relative motion. Why did I solve this? I don't know. I mean, this kind of an arrangement is actually used in the famous Michelson-Morley experiment, in which case, yeah, let me not talk about this thing, right? But in the case of Michelson-Morley, you would like to measure the speed of light relative to something else. But since you are on Earth and Earth is moving, so probably relative velocity of the light relative to us might be different from its real velocity. So in any case, it was one of the famous experiments in physics. And it's the one that, I mean, its negative result was actually quite important for the development of the Einstein's theory of relativity. But in any case, I mean, this is something that you're going to see in modern physics, and you're going to see these kind of calculations over there, right? Just keep this in mind. Okay, so I don't have much in here. So there's this wolf and sheep problem. Since these are classical problems that I actually solve all the time, so I know that there's a solution of these in the previous year's videos. So it should be part of this current chapter. So I'm also going to check the videos, and I don't know if, I mean, if it isn't there, then I'm going to prepare a video and add to that list. Okay, just keep this in mind. Since it's like 10:20, I have to stop now. Yes, ether. Right, so there was a different kind of a theory at that time. All right, but this is an example of a two-dimensional problem. So still, there's an airplane problem as well. So, I mean, an airplane is flying, but the air is also moving because of the wind, for example, in some certain direction. So as a result, you have to move in some certain way so that you can reach to your destination. Okay, so I'm not even going to read the problem. I'm not going to solve anything, but as I said, I mean, if it appears that I haven't solved any problem in the previous year related to this two-dimensional relative motion problems, I'm going to prepare a new video and then place it on YouTube. Okay, but if it is there, then I won't do anything. Okay, so let's finish it here.